Hey, this is Jason Smith and Mark Fry. We created fiber plastic insulation and we tested to figure out what the K value, the thermal conductivity of the fiber plastic is, and then we solved for an R value to compare it with other current insulation.
The inspiration for this project was given to us by Brother Kinghorn when he was talking to us about the billions of bottles of plastic that are wasted every year and not recycled. So we were thinking, what's some sort of product we could make out of these plastic bottles?
We decided we could make long fibers and use those long fibers to create a composite that is a insulation out of plastic water bottles. Taking the fiber, we're not going to disclose the information on how to create the fibers themselves, but we took the fibers and did create the insulation, and the reason we're not disclosing it is because we do want to pursue a patent.
So, home insulation, in order to be used in the United States according to US building codes, must meet a certain R value. Before we started this project, we were shooting for an R value of 13, which would mean we could use it in zones 1 or 2, so very south of Florida, the Pacific Islands, Florida, and Texas, for floor insulation. That's really the value we were shooting for.
Hey, how's it going? Right here, we have our heat transfer project. So what we did is we made insulation out of plastic water bottles. In this contraption here, we made our own homemade insulated box that covers the door of a toaster oven. So what we did is we made this cube, 5 by 5 by 4 inches thick cube of insulation, and it's placed within this insulation here, this foam insulation. On the inside, we put a thermocouple, and it's reading the inside of the toaster right at the back side of our insulation at 178 degrees Fahrenheit. Now, if you look in here, we put our insulation and we cut out this square tube here. Right on the back side of this piece of cardboard is our insulation, and we have a thermocouple right now reading the temperature between our insulation and the cardboard, and it's reading 89 degrees Fahrenheit. So all the heat that is going through the insulation is being absorbed, or our insulation is blocking the heat, and it's only a couple of degrees hotter than it actually is outside. We can switch the thermocouple to number 3. Let's see if I can get it. Number 3, the thermocouple labeled 3, is this thermocouple in the top right corner behind our cardboard. So that is the ambient temperature on the back side of our cardboard, which is still 86 degrees Fahrenheit, the same as the inside of that one layer of cardboard.
So the fiber plastic that we were able to make fit inside of a cube that was 5 inches by 5 inches by 4.5 inches. It weighed about 33 grams, and that was with the included fire retardant spray that we put on it, which is required for all home insulation. It came out to a density of about 2.93 grams per cubic inch, and that is roughly twice the density of a similar kind of fiberglass bat insulation. So we knew just based on size and weight alone that our product was very similar to what is on the market today.
Temperatures were measured by each thermocouple at different points during the project. The temperatures are measured in degrees Fahrenheit, and T1 represents the temperature on the inside of the toaster oven right up against our insulation. T2 is the back side of the insulation right before the cardboard. T3 is on the back side of the cardboard that is exposed to the temperature outside. And T4 is the same, just in the corner rather than in the center. The important column to focus on is T2. That is right behind the insulation after the heat has traveled through our insulation. And you can see, comparing with the inside temperature, for example at 143 Fahrenheit, the back side of the insulation is 83, meaning our insulation is actually working, blocking the heat from going through our insulation.
So in order to determine the heat transfer through our material, we needed to come up with a resistance network through our plastic insulation and through the cardboard. By measuring T2 and T3 of the cardboard, we were able to determine a Q value going through our whole network of 0.209 watts.
Once we had our Q value, we can use that to determine the K value of our insulation. We solved for our K value knowing the temperature of the oven and the temperature at the back side of our insulation. We solved for our K value and came up with the value of 0.020976 watts per meter K.
And this is a really good value because the K value for fiberglass insulation is about double that. So that means our material resists heat even more than fiberglass insulation. So we were able to determine our constant of K. Now in order to change that value into a useful value by which insulation is measured, we needed to convert it to what's called a RSI value, which is the inverse of the K. Then you multiply that by the length of the insulation that you used. Ours was 4.5 inches. And then divide by a constant of 5.678 to get it into the insulation units, which gave us an R value of 26.63, which is about twice as good as what we were shooting for at an R value of 13.
The R value was converted from an RSI to an R value for the US building code. We used US English units. So according to our value, we can use this insulation for ceiling insulation in zones 1, 2, and 3. It can be used in any floor. It can be used in any exterior wall.
So overall, we're very happy with how our insulation turned out. And the numbers really show that this is a very useful product, and we learned a lot about insulating materials through this project. Thank you very much.